Hello everyone, how's it going? My name is Dan the Tutor, on a mission to become the world's greatest tutor. In today's video, we're going to be talking about position, velocity, and acceleration in calculus and how they're related to each other. So the short answer is, let me just draw some bubbles here. We have these three concepts in calculus: position, velocity, and acceleration. These concepts also exist in physics, which I can cover in a different video. But we're going to be talking about these from a calculus perspective today. And so I'm assuming at this point you know what the derivative is. Remember, derivative is just a fancy word that really just means slope. But in this context, we're going to use another definition. We're going to call it rate of change, which is technically what a slope is anyway. And so the reason why this matters is because if I were to describe velocity, like a technical definition of velocity, I would describe it as the rate of change of position. And I would describe acceleration as the rate of change of velocity. And so what that means is we have this relationship between the three, and here's what it is. If you want to go from position to velocity, then all you have to do is take the derivative, which this is my symbol for derivative, d over dx, or maybe I'll just call it f prime of x, because that's probably what you like writing anyway. And then if I want to go from velocity to acceleration, well then I have to take the derivative again. Now we're talking about the second derivative, which would be f double prime of x. And so long story short, if I want to go from position to velocity and velocity to acceleration, I'm either going to use the derivative, or if I'm actually given a graph, I will use the slope. Especially if it's a slope I can compute very easily. Like if it's a straight line, for instance. That's very easy to find that slope. Now really that's what we're going to be focusing on today, is this forward relationship. But you should know in calculus we can go backwards as well. In other words, I can go from acceleration to velocity and velocity to position by using the integral, which is the antiderivative or the opposite of rate of change. But we're not going to be talking about that in this video. I'll cover it in a different video. But just know that it is possible. So let's do a couple problems now. Let's say for my first problem, I have a position function, x of t, which is equal to 3t squared minus 6t plus 5. The units will be meters. And let me ask a three-part question now. Part 1, I want you to find the velocity at time t equals 2 seconds. And I guess we'll just start with this before I give you parts B and C. So if I want to find velocity, it's very easy. I'm just going to take the derivative. You can do one of two things. You can either write x prime of t for velocity, or you can write v of t. The professor usually accepts both of these. I'm going to be using x prime of t. That's my personal favorite. And the derivative of this is just an easy series of power rules. It's going to be 6t minus 6 plus 0. So I don't even have to write plus 0. Hopefully that makes sense. I don't have to explain it because I really don't want to. I'm assuming you know this already. But now if I want to find the velocity at t equals 2, and here's the velocity function, then all you got to do is plug in 2. 6 times 2 minus 6, 12 minus 6. I'm going to get 6. What are the units? It's a velocity. So in other words, in this case it's meters per second for velocity. So that's it for part A. Next for part B, let's find the acceleration at the same time t equals 2 seconds. So if we start with the first derivative, which is a great place to start, 6t minus 6, then the acceleration is just going to be the second derivative. So we just take the derivative again. This is very simple. It's 6. Now this is the part where kids usually get confused, because I have 6, I have the acceleration, but how am I going to plug in t equals 2? And the answer is you're not. It's kind of a trick question. Because there's no t, the answer is 6. The acceleration is 6 everywhere, at every time. Whether t is 2, 5, 10, whatever, the acceleration is always 6, and the units are just going to be meters per second squared for acceleration. And so that's the answer for this one. And now let's ask one more question here. For the next one, I want to know if the object is speeding up or slowing down at t equals 2 seconds. So how are we going to answer speeding up and slowing down? It's very easy. You just have to look at your velocity and your acceleration. If your velocity and acceleration have the same sign, in other words, positive, or they're both negative, that's when the object is going to be speeding up. And then whenever velocity and acceleration have opposite signs, in other words, one's positive and one's negative, that's when your object is going to be slowing down. And so then how do we know if it's speeding up or slowing down at 2 seconds? Well, we're basically going to take our answers from parts A and B. The velocity at 2 seconds was, if you remember, 6 meters per second, positive. The acceleration was also positive 6. What a quinky dink. And since they are both positive, it is going to be same sign, therefore speeding up at 2 seconds. And there we go. That's it for this question. We're going to do one more, but this time I'm going to ask a different series of questions. So this time I have an object moving in the y direction. Y of t equals negative 16 t squared plus 32t, and the units this time are going to be feet and seconds. For part A, I'm going to ask, when is the object at rest? Very famous question. Well, what does it mean for an object to be at rest? It means its velocity is equal to 0, right? And we know velocity is really just the first derivative. So the first thing we're going to do is take the derivative. So derivative of this will be, again, power rule, negative 32t plus 32. And now all we're going to do is set this equal to 0, and now we're going to solve for t. So I would add 32t to both sides. The 32's cancel or divide by 32. Regardless, you're going to get t equals 1. So in other words, the object is momentarily at rest at t equals 1 seconds. Don't forget the units. Very easy to lose stupid points with that. But that's the answer, t equals 1. And so in other words, if we think about this object as like a kid or something throwing a ball up and then it comes back down, basically what we just discovered is that for the object to get from here to here, it's going to take a time of 1 second. I'm not going to ask about how long it takes to come back down, but if you ignore air resistance and you're ending at the same place where you started, which is normal for these problems, then that would also take 1 second to come down as well, and you can prove that if you'd like, or you can take my word for it. Regardless, that's not what part B is going to ask for. For part B, I'm going to ask, what is the peak height? Now this question's obviously a little trickier. So why don't you pause, think about it for a second, and time's up. So when I ask for the peak height, remember the peak height happens when the object stops at the top. And we know when it stops. It stops at t equals 1. But what am I going to do with that time? Am I going to plug it into the original function or the derivative? I'm going to plug it into the original function. How come? Because the original function represents what? Position. In other words, height. If I wanted to find velocity, then I'd plug it into the derivative. So anyways, what is the peak height? All I have to do is plug in 1 into the original function right here. So negative 16 times 1 plus 32 times 1. Don't even need a calculator for this. It's going to be positive 16. And the units are feet, not feet per second, because we're still talking about a position, a height. And so then the last question I'm going to ask for today, what is the acceleration at the peak height? So in my opinion, you should be able to do this on your own now. So why don't you pause the video, give it a try, and when you're ready to see the answer, unpause. Okay, so we need 2 things for this problem. Number 1, we need acceleration, which of course is going to be the second derivative, which I'll find in a second. The second thing you need to know is, where is the peak height happening? So we need a time. And we actually know the time already. It was at 1 second. That's when it reaches the peak height. So all we really need is the acceleration. So the first derivative we remember was negative 32t plus 32. So then it looks like the second derivative would just be negative 32. And like we said before, since there is no t, it doesn't even matter what the time is. The acceleration will always be negative 32. Units are feet per second squared for acceleration. And that's it. We're done. So hopefully you don't have any questions with that. If you do, please post them in the comments. Thank you all for watching. Have a great rest of your day. And I'll see you in the next video. Take care and bye-bye.